Have you ever found any incomplete data in your dataset? Missing values are everywhere. They occur in almost, if not all, real-life time series datasets. Sometimes we can just remove them and go on with our analysis, but sometimes we have to fill them in because otherwise we won't be able to use the data at all. When it comes to imputing missing values, the basic approach would be something like filling them with zeros, the mean or the median. We can also do forward filling or backward filling. More sophisticated methods would include interpolation and other methods. We learned to use the dynamic linear model before for the same task, but now I want to try another method. Welcome back to my channel. In today's video, we're going to impute missing values in a time series dataset using singular value decomposition or SVD. SVDImpute, as we can see here, is the name of the algorithm. SVD is a concept that we have learned at the introductory level of linear algebra. So it's going to be interesting to see how a basic concept can be powerful in addressing this task. So more concretely, we will first learn how SVDImpute works, then apply it to fill in the missing values in PM 2.5 time series. Alright then, let's study together. Let's say we have a multivariate time series like this, where we arrange each time series vertically so that the rows represent the timestamps and the columns represent the variables. Then this might be obvious, but when I say an observation, it means a reading at a certain timestamp. Each observation is a data recorded at a certain time unit. Okay, now let's call this dataset matrix A. I will denote the time as m and the variables n. So matrix A has the dimension of m rows and n columns, or m by n. Now, in linear algebra, by applying SVD, we can break down, or more formally factorize, this matrix into three matrices: matrix U, sigma, and matrix V transpose. Matrices U and V transpose are orthogonal. Matrix sigma is a diagonal matrix that contains the singular values of matrix A. Singular values are the square root of the eigenvalues of matrices U and V transpose. So sometimes we can sort of like loosely speaking that the diagonals in the matrix sigma are the eigenvalues, even though that's not correct. Anyway, now let's take a closer look at this matrix, matrix V transpose. Each column of this matrix is an eigenvector of the matrix A transpose times A. And this n by n indicates that the dimension of matrix V transpose is n by n. Now, if we look at this time series dataset, we have 5. So let's pretend that n is 5. Okay, let's go back to this. So matrix VT might look something like this, where we have 5 rows and 5 columns. Each column is called the loading vectors in principal component analysis. So we can also think of them as the principal components. I mean, in statistics, principal components usually mean the loadings or the directions of the eigenvectors. So yeah, let's name the columns E1, E2 until E5. Okay, and the rows represent the variables now. Okay, so let's say that the first row is n1 because variable I denote the variable as n, right? So the first row is n1 and then n2 up until n5 here. Okay, so this is the first step of the SVDImpute algorithm, doing this SVD. Actually, there's one thing we need to do before SVD, and that is substituting row average for all the missing values in the matrix A. We have to do this since SVD can be done only in complete matrices. The next step is sorting the eigenvectors based on their eigenvalues, which are in the matrix sigma. So matrix VT, let's say that E1, E2, E3, E4, and then E5. in the next step, we are sorting the eigenvectors from the most important one to the least important one. So let's say that perhaps the most important eigenvectors turned out to be the third eigenvector. So E3, and then E1, E2, and then E4, and then E5. Let's say it's like that. And for the rows, they are not changed. So it's still N1, N2, N3, N4, and 5. Okay. The next step is to take the k most important eigenvectors. So we will get a reduced matrix V. The dimension would be n by k. So let's say that we want to take two most important eigenvectors or principal components. In other words, we set k equals 2. Our reduced matrix V would look something like this. So we have 5 rows still, but for the columns, we only have 2 columns that are E3 and E1. That means when we set k equals 2, we just take the first 2 columns of the sorted matrix Vt. This reduced matrix Vt is used in the next step, that is the imputation. Oh, I forgot to tell you, the orange boxes in this matrix show the missing values. So like in this observation, we have only one missing value, and for this one, the last observation, we have 2 missing values. And then for this observation, all variables are missing. Now for this row, this observation, SVDImpute cannot help us. Yeah, this is the limitation of this algorithm. SVDImpute cannot help us when we have all variables missing. I think this makes sense. I mean, if all values in a row are missing, then how can we set up the linear regression equation? How can we take the row average to replace the NAs as in the step, like the very first step before doing the SVD? But if we have at least one observed value in one observation or in one row, then SVDImpute can help us. Okay, so for this case, I will do forward filling. But now let's explore how the algorithm works when we don't have that situation. The imputation of a missing value j of observation I, let's say that we want to impute the missing value from this observation, so this is an observation I. The imputation is done by regressing the observation against the selected eigenvectors or the reduced matrix V transpose. And the variable with the missing value will not be used for regression. What I mean by regressing the observation, that is the observation I here, this observation has 4 observed values, right? So this observation becomes the dependent vector, okay, or like the y. In regression, this should be really familiar to us. So y equals the predicted coefficients times the input or the independent or the regressors. Our observation I becomes the y. And this vector has 4 values because in this particular observation I, we have 4 observed values. And then our theta hat, and then x. Now our x is the reduced matrix V transpose. Now recall that our matrix Vt, the reduced matrix Vt, has 2 columns and 5 rows, n1, n2, n3, n4, n5. But since we want to impute the first variable, we have to remove the first row of this reduced matrix. So our x would be a matrix of 4 rows and 2 columns. So E3 and E1 are still here. And then for the rows, we don't have N1. We don't have N1, but we use only n2, n3, n4, and n5. So as you can see, for each missing value, we will have slightly different regression problem. So like for this one, for the last observation, let's erase all the inks first. So for this last observation, again, y equals the theta hat times x. Our y would be a factor of only 3 values. Okay, now that we have only 3 observed values in this observation. And then the theta is still the same. And then for the x, we will have 3 rows and 2 columns. And for the rows used would be n1, and then n4, and n5. We don't use the second and the third row of the reduced matrix V transpose because they are the missing values. And then the obtained or the trained theta hat would be used to reconstruct the missing values. So continuing our example, the trained theta coefficients would be an array of length 2 because we have 2 columns here. So 2 features. To reconstruct the missing values, we have to do dot product between theta and the removed part of matrix V transpose. Okay, maybe I'll just write it as V transpose and A. Something like this. If we have only one missing value in this observation, for example, like this one, where we want to impute the missing value from the first variable, theta would be an array of length 2. And then the matrix V transpose that was removed before would be the first row of the complete matrix V transpose. But we have to transpose it again so that the shape matches. So it will have one column that is the first row, by the way, of matrix V transpose, and 2 rows because of the 2 eigenvectors. Okay, if we go back to this example, that means our theta would be again an array of length 2, and the matrix V transpose and A will be 2 columns and 2 rows. 2 columns and 2 rows because the rows are for the eigenvectors and the columns are for the variables. The point is that the part of matrix V transpose that we want to take is the one that we just removed. So this is like saying that the first coefficients is for the first variable, or for the first eigenvector. That's why we have to align the eigenvectors along the rows. And then for the second value in theta, this is for the second eigenvector. So we have to align all the values in the second eigenvector along the rows. So yeah, that's how you get the imputation. This imputation is done for all missing values in that matrix. So after we complete the imputation, we will get a new matrix. But of course, since this particular observation has all missing values, we are not applying SVDImpute actually to this. That's why I give a different color. Okay, but anyway, we get a new matrix. Then we repeat the process. We keep repeating the process of breaking down the imputed matrix, sorting the eigenvectors, taking the k most important ones, and doing the regression for the originally missing values until the total change in the matrix falls below a predetermined threshold. By default, and this is the value used by the authors, the threshold is 0.01. And the total times we repeat the process is called iteration. And so this is why I give the number 1 here, because this matrix is the output of our first iteration. Let's say that we have 100 iteration, and so the last output would be A100. This is the final output. So the final output of this algorithm is the matrix outputted from the last iteration. This matrix, this A100, represents our dataset, but without the missing values. Okay, so that's the summary of the algorithm. Now, before moving on to the coding section, I want to show you the function we will use to apply this algorithm. We are going to use R to apply this algorithm. Its implementation is available in the package PCA methods, and the function is this. We can call the function SVDImpute directly, but that approach is not recommended. The better way is to call the function PCA, then put the SVDImpute as our method. I'll explain more about this, the difference between this function and the previous one, this one. But now let's see the data for this use case. Okay, now here we are in our RStudio. First things first, loading the necessary packages. Here is the PCA methods package, which has the algorithm implementation. Next, let's talk about PM 2.5 for a second. PM 2.5 is particulate matter. Loosely speaking, that is a really fine dust which diameter is 2.5 micrometer maximum. This indicator is commonly used to understand the level of air pollution. So the higher the value means that there are more dust in that area, so higher pollution. Our PM 2.5 data is from the Bogotá Air Quality Monitoring Network. I'll use the same dataset from my previous project, linked here for reference. Now we load the dataset. And save it as DF, then change the data type for the column date time, and rename one of the variables. That variable was originally ozone, but in Spanish, or maybe in Brazilian, I'm not sure. Anyway, this DF has the measurement for all stations in Bogotá. The list of the stations are here. But to simplify the project a little bit, I chose the readings from only one station, and that is the station LFR. So I named the subset A to make it consistent with the theory. Okay, let's run the cell. Here, by running the function str in R, we can take a glance of the subset A, and from this we can see that A has around 8,700 observations. This is an hourly time series for a year in 2021. So as we can see here, the date time here, the first value is this, and at 1 a.m. and then the next is 2 a.m., 3 a.m. and so on. There are other measurements other than PM 2.5, such as PM 10, and then nitrogen monoxide, nitrogen dioxide, and so on. In this cell, I make the time plot for PM 2.5, the time series we want to impute. So here it is. Okay, so this is the time plot, and perhaps it's a little bit hard to see the gaps, but we can see one here. Let's zoom in. Okay, so like here, January 25, we have around 8 hours of missing values. A longer period of missing values occurred here on January 22. So this is January 22, but the next observed value is on January 25. So the missing value lasted for around 3 days. I also plot the scatter plots of pairs of variables in the dataset. Here we can see a clear and obvious correlation between PM 2.5 and PM 10. We can see strong correlations among the nitrogens as well, like for example this one, NO and NOx. Okay, and then I tried to calculate the total missing values in this dataset. In A, we have 254, which is quite small, considering that we have 8,000 of observations. Let's see. yeah, the missing values is only 2% of the whole subset of the whole matrix A. Okay, and then lastly, I just want to see if the missing values occurs more frequently at a certain time. If we have 254 missing values and we have 24 hours a day, that means if we want to have a completely random missing values, then each hour should have around 10 occurrences of missing values. But here we can see that the missing values occur the most at 7 a.m. and at 12 p.m. And I think the NAs generally occur more frequently in the evening than in the midnight. Okay, now that we have seen the data, we need to do the final preprocessing so that our matrix can be processed by SVDImpute right away. There are several requirements we need to check. Like for example, we need a numeric matrix. So we cannot have a vector of characters or any other data type. That's why in this line 75, I removed the last two columns in that matrix. They are the station identifier and the date time. The next requirement is that we cannot have rows with all missing values. So like I illustrated earlier in the theory section, we cannot have a row with all orange boxes. And to check that, I make a little function in the next line 76. And well, let's run this first and then run the function. And then here we can see we have 22 such rows. And for these rows, we're going to do forward filling. That is in this line. Okay, now this requirement is already fulfilled because we don't have any more rows with all missing values. And then the next requirement is that we cannot have a column with all missing values. So basically we cannot impute a time series that is originally empty. Alright, I guess that makes sense. And even though I haven't shown you, okay, let me show you the matrix A now. After removing the last two columns, we can see that we don't have any column with all missing values, because if that's the case, we will see a column of all NAs right from the first page. Here are the first 10 rows of the matrix, and other than these two NAs, we have all the data. So that requirement is already fulfilled. Okay, so now our matrix is ready for imputation. Here I showed you the non-recommended way, that is by using the SVDImpute function right away. So running this won't give us any error. Let me run this line only. See, it gives us the change in estimate, which is, by the way, the total change. It can run the imputation normally and no error. And we can even look at the summary of the object, but we won't get anything. We won't get the imputed data. So to get the imputed data, we have to run the object of the imputation, which is here, direct imputation, and we put it into the complete observation function. As we can see, running this line will give us nothing. And yeah, that's why we cannot impute it using SVDImpute function. Now, the right way to do it is by using the PCA function and then put the SVDImpute as a value in the method argument. And then this is a little bit different from what I showed you earlier in the slides, but I use the CV and type arguments. Okay, and by the way, this scale argument is for scaling the data. I'm using the Pareto scale method, that is the square root of univariate scaling method. And then the argument for centering the dataset is also here, actually. It's also available, but its value is true by default. So I'm not changing that. That's why I don't write it here. But for the scale is none by default, so it doesn't do any scaling. But I decided to do one. I decided to do burrito because I thought this is basically like PCA, principal component analysis. So I thought, well, the standard practice in PCA is to standardize and basically normalize. So take the mean and the variance out of the dataset. Okay, now what is the CV argument? We don't know how many principal components we want to take. So I'm going to use cross-validation to determine that. And the metric to compare the models is Q squared. So Q squared is the cross-validation version of R squared. R squared is the variance, the proportion of variance explained by the principal components. Okay. And then the type here, this argument is actually for the argument in the Q squared function. I'm using the impute because we have missing values in our input matrix A. Okay, let's run this. Again, the change in estimate here, I don't know if it's clear. Oh, okay. So the change in estimate here is the total change in estimate between the last matrix and the previous matrix from the previous iteration. All right, now we can gain some information out of complete PCA object. The first is sdef. By running the sdef function, we can get the eigenvalues. And we can see that the eigenvalues are sorted. So the first principal component is the most important eigenvector because it has the biggest eigenvalue. Okay, and then we can also plot it. We can also plot the object right away, and this is what we get. The R squared and, like the bar plots of R squared and Q squared, but I'd like to do it like this. Okay, so here we have 3 lines to plot, but actually the first 2 lines are exactly the same. So I just want to show you that we can get the Q squared values in 2 ways. The first is by running the CVStat function. We can do that because we already specify the CV in the PCA function. Okay, and then the second way is the more direct one, that is by running the Q squared function. And see the type impute here is exactly the same as here. And then nrun CV is the number of CV iterations that we want. The default value is 1. I am aware that the better practice is to have more than 1 run. And I tried to run it 5 times, but I get the same result. So let me show you. Let's say that we run it 5 times and see the result. Okay, now we have the Q squared scores for each principal components in each iteration. So the columns represent the iteration, and we can see that they are exactly the same. So that's why I run it only once. Now let's take a closer look at this plot. And so, as we can see here, the Q squared scores is exactly the same, no matter which function we run, right? So I'm going to remove the gray line now so that we have only 2 lines, the black line, which denotes the Q squared scores, and the red line, which is for the R squared, the cumulative R squared to be exact. And then the x-axis, this is for the number of loadings or the number of principal components. Okay, so when we have only one principal component, that single principal component can explain 66% of the whole dataset. This is what the R squared is telling us. Okay, and then for the Q squared, this is like R squared, but the cross-validation one. The lower the Q squared, the less meaningful the principal component in trying to explain the whole data. And looking at this plot, I want to use 2 and 3 principal components later. So I want to try using 2 different values for k, that is 2 and 3. Why 2? Because using 2 principal components, we can get the highest q squared, that is 0.61 here. But using 3 principal components, even though the q squared value drops a little bit, we can get quite high or like decent cumulative r squared. So the 0.92 here means that using 3 principal components instead of using 7, we can explain 92% of the whole dataset. That means if we use 3 principal components or 3 variables, we have a better chance of getting good imputation. Why not 4? Because using 4 principal components give us a quite low q squared. Yes, we can see the q squared from using 3 to 4 principal components drop a lot. And the r squared, the cumulative r squared, doesn't improve that much. So yeah, I'll stop at 3. Okay, now the next thing I'm going to do is running the PCA function twice. The first is using 3 principal components and then 2. After running the PCA function, I store the object in PC3. That means I'm using 3 principal components, and then put this object into the complete observation function to get the imputed data. Let's run this chunk. And then, yeah, we can get the summary of the object. This is quite similar, similar with if we just run the PC3. Anyway, I also add the line plot of this imputation to our time plot earlier, but we're going to save that for later. Now, I want to get some insights from this object before looking at the imputation plots. Okay, so first of all, we can get the r squared cumulative from PC3, and we can just plot it. This is actually similar to this, so the cumulative r squared, 0.67, 0.85, and then 0.93, and yeah, that's what we have in this plot. Okay, and then we can also plot the principal components side by side by using this function. So we have different names for principal components so far, right? Like the columns of matrix V, and then the loadings, and then principal components. Another name for that is the new coordinate system. Now recall that the columns of matrix V are orthogonal, so they can be seen as the new coordinate system. And so these 3 plots are the scatter plots of the data using this combination of principal components. And then we can also get the r squared, or the proportion of the variance explained by each principal component. Next, we can run the SL plot, which is the scores and loadings plot. Okay, so we have the scores plot and the loadings plot side by side, but this is only for the first 2 principal components. So continuing my other view of loadings as the new coordinate system. If we project our original data in the Cartesian, the original coordinate system, which center is all 0, we project those data to our new coordinate system, we will get the scores. And then for the loadings plot, here we can see the direction for each principal component. This is basically the linear combination of the variables. So ozone is 0.2 times principal component 1 minus around 0.4 times PC2, and so on. And then by running the SDEF I already showed you earlier, this can show us the eigenvalue. And I just want to show you that running SDEF of PC3 is actually the same as applying the standard deviation of each column in the scores of PC3. Okay, as we can see, they are exactly the same. Okay, and then the next is loadings. I said earlier that the loadings are the columns in matrix V, so I tried to compare the loadings with taking the matrix V from the SVD function. Now, as we can see, we have slight differences, but maybe this is because we run the SVD function and from which take the V matrix from the imputed matrix, the imputed data. While for the loadings, I guess the loadings here is from the loadings of the previous iteration. So like the last iteration before generating the imputed data. Okay, so what I'm saying is that perhaps we talk about two slightly different matrices after all, which explains the difference in these results. But I can show you that the loadings is indeed the columns in matrix V, and I want to show you by running these three lines. So we have a data set that is in R already, that is called rand_u. So I run the PCA function using the SVD method, and then I also run the SVD function for the centered and scaled dataset, the rand_u, and then compare the loadings and the matrix V. They are indeed the same. So yeah, if we change the method into SVDImpute, let's see. Yep, we still have exactly the same. Alright, now in line 127, I said earlier that if we project the data into our new coordinate system, we will get the scores, and here I want to prove that. So other than the NAs, we get the exact same result. Okay, I mean, like the NA is natural, only natural here, because we are multiplying the A, the original matrix, with the loading. So of course we get NAs. Okay, now let's move on. I'm going to run another PCA function, but this time for two principal components only. I just want to check the dimensions here. The dimension of the loadings is like the dimension of the reduced matrix V transpose, that is 7 rows for 7, that is for 7 variables, and 2, that is for 2 eigenvectors. Again, then the dimension for the scores, because the scores is actually the data set itself, but projected to a new coordinate system. This is the dimension. We have 8,760 rows. That is the total observation or the total time steps in our time series. And we have 2 columns, that is for the 2 principal components. And then the dimension of complete observation is 7 columns instead of only 2, because again, SVDImpute does the imputation for all variables. All right. Okay. And now let's see the imputation. So I'm going to show you the original data and then the imputation using 3 principal components and using 2 principal components. Okay, let's see, around January 22. That's the missing value we saw earlier. So the yellow is for the imputation by 2 principal components, and then the blue one is for the imputation using 3 principal components, and the green one is the original data. Okay, now let's see here. Like this one, this is January 23 at 6 a.m. The green, look at the green box there. It doesn't move along the blue and the yellow boxes. So this is telling us that this is where the imputation happens. Okay, maybe we should enlarge. Okay, so this is the missing period. And let's see, if we impute it using 3 principal components, this is what we get. We don't get a straight line, like if we use the basic imputation method, like for example, filling it with the mean or the median. So visually it looks nice. Okay, and now let's compare it with the 2 principal components. It looks quite similar. Right, now we can see that, yeah, they are indeed really similar. Sometimes the imputation using 3 principal components is higher, and sometimes the other way is true. Unfortunately, there's no valid way to scientifically measure the accuracy of the imputations, as we're dealing with real-life missing data. Of course, we could have trained SVDImpute on a complete time series, like on a complete subset first. If we want to do that, we take a complete subset, like maybe the end of the time series, and then we randomly take some values. So we create the missing values and then try to impute them using SVDImpute and see the accuracy. But I don't know, this might be an unpopular opinion. I sometimes think that we really need to lean more on the visual means. Just plot them out and see if they make sense. Like in this imputation earlier, it makes sense because it doesn't look like a straight line. Like it can't be a straight line. We cannot have a constant PM 2.5 for 3 days or even for 2 hours, right? It keeps changing. This is a dynamic world, so we almost always cannot have a constant value or like even really similar value. That's why like having straight lines doesn't really make sense. Yeah, I'm just stating my personal opinion here. Okay, and then this is, well, I tried a little experiment here, even though, yeah, as we will see in a minute, it's not going so well. So I tried using less variables. I tried using only PM 2.5 and PM 10 because these two are the most highly correlated. I mean, we want to impute PM 2.5 time series, right? And the other time series that has the highest correlation with PM 2.5 is PM 10, naturally. So I try to impute the missing values in PM 2.5 only with these 2 variables. And the imputation using that method is denoted with the pink line. Okay, now I haven't even zooming on anything, but we can already see some differences. Okay, anyway, let's look at this. Let's zoom in at the same period. Okay, yeah, so here, okay, let me zoom in even further. Okay, on January 22, we can see some straight lines, while the imputation by 3 and 2 principal components fluctuated a lot. Yeah, I guess, well, 13 is the median, or I mean the mean of the PM 2.5. Maybe that's why we get this imputation. We can check the center by using the center function. Yeah, as we can see, 13.25, that is exactly the mean, and that's why the imputation, the missing period is imputed with that mean. But if I remembered correctly, it's not always like this, actually. Wait, let me see. Like this one. On February 4, we have another missing value. Let me zoom in again so we can see better. Here, February 4, 11 a.m. This is the last hour before the missing period. Okay, so at 12 p.m., the imputed by 2 and 3 principal components show us, well, really similar value, 5 and 4. But for the imputed by 2 variables only, we have 16.8. We cannot say that this is worse actually, but my point is that 16.8 is not the mean. And actually looking at this, we might... Wait, let me show you a better view. Okay, let's take a look at this. Actually, if we focus on the pink line only, it looks okay for this period only. Like if we remove the pink line, well, I don't know, visually it looks okay. This is the original data. We can see the missing value. If we impute it using only 2 variables, we get it like this. But if we say impute it with only 2 principal components but 7 variables, this is what we get. Again, at the end of the day, we cannot really choose which one, but I will personally choose either the imputation by 2 principal components, the yellow line, or the blue line, because in general, the imputation makes more sense. Here, I tried to take the ACF, the autocorrelation function, from each imputation and with the original time series, and we can see that they are really similar. So I guess this is saying that the imputed series is really similar with the original. I mean, like, if the imputation is really bad, then supposedly the ACF would be different as well, right? The same goes for PACF. We get really similar, even with a cyclical pattern here. We get to see that as well. So that's it for today's video. Thank you so much for watching. I'll put this code in my GitHub and Kaggle. If you are interested in learning more about time series analysis, please consider subscribing to my channel, Timely Time Series. I'll see you next time. Bye-bye.